for our August meeting. We have Prasanth Sahoo, who is going to present to us on validation of frequency domain ship motion. We'll hear a lot about, I guess, heave and pitch and all other motions, which is appropriate. Prasanth is speaking to us. He has joined us on staff at the University of New South Wales, Canberra in the Naval Architecture Group just this year in April, after time at Florida Institute of Technology, and prior to that at AMC, the Maritime College in Launceston. And prior to that, if we go back to Germany and India, but if that's relevant to tonight's presentation, I'm sure Prasanth will give us the details that are appropriate. I think the presentation has some links back to his work at AMC in the past, but I'd like to welcome him this evening, and we look forward to your presentation. And I'll just remind you to turn your mic on.
Yeah.
Thanks.
Thank you. Can you hear me? Yep. All right. Back to this podium, right, after a long time. Now it's similar to giving lectures at AMC. So nice feeling here. So what I was planning to say was that besides teaching only the hydrodynamics for a number of years at AMC, did that at Florida Tech, then I went on to teach at on sabbatical leave at UBC, this University of British Columbia in Vancouver, then also at University of Liège in Belgium. So been there teaching the same thing. I'm getting a bit tired of teaching the same thing all the time. Anyway, this is going to be slightly different. This is a paper which has been written with my co-authors from Yildiz Technical University in Turkey for the PRATS 2022 conference in Croatia. So that conference will be held in sometime in October. So coming back to this problem here, what we have done here is nothing innovative here, I can say that. But you know that predicting the ship motion is a difficult problem. We all know that, and we are all engineers. We want something fast, something accurate, something more reliable to be done instantly. I mean, we don't have time to wait to learn the software, apply the software, and get the motions and see whether these motions are likely to be correct or wrong. Who knows what is happening here? So that is why we thought that some sort of a validation is required to make sure that what we are doing is actually right. And so far, you'll find a large number of research papers on ship motions in the published literature. And you will find that not only we have gone from strip theory, which is essentially a 2D method. There's a 2.5D method and 3D methods, and then CFD has come in. So you'll find a really large number of papers, and there is no time and patience to go through all these papers and see what is happening here. But however, just to give you a brief history behind this ship motions, what really happened, that most of us are probably familiar with existing softwares that we use. Universities are also in the industry, and that is the strip theory method, which is essentially a cross-flow hypothesis first initiated by Lewis, but based on the work by Corbin, Krukowski, and Jacobs, which was applied to ships. The underlying principle behind this strip theory is that the wave profile remains the same across the sections over the length. And that is somehow came to be known as the Fruit-Trilop hypothesis. And subsequently, we know that there was a remarkable paper by Salvesen, Tuck, and Faltinson in 1970 in SNEMI transactions, which gave a lot more information. And that theory was that paper has been cited by anyone who does ship motions has to cite that paper. So I'm also citing that paper. That paper actually was to validate the motions and seems to give actually very good results as long as heave motions and pitch motions are concerned. And based on that, there was, however, the we have this lateral motions, especially sway, yaw, and roll. And they can be, the correlations can be as good as what we get from experiment to be good, depends on how theory can actually look at the auxiliary control devices in the theory itself. So, however, strip theory is also essentially used for calculating the forces and moments. And they are based on a range of papers first published by Ursel somewhere in 1949. And Ursel was dealing with circular cylinders, the heaving motion of circular cylinders in sinusoidal waves. So there, he found that the stream function should satisfy the linear boundary conditions on the wave surface as well as on the oscillating cylinder itself. And the second method was actually a source singularity method, which is rarely used here. So in both cases, both velocity, potential, and stream functions have to be determined through analytical methods. So I'm leaving behind all those mathematics which were there behind. I'm not going to tell anything about those things. Now, because Ursel was dealing with circular cylinders, so for the transformation of the shape, which is not a regular cylinder, should now be transformed into circular sections by some means, so that the boundary conditions are held or remains unchanged or kept fixed as before, just like for a circular cylinder. So this gave rise to two sets of what is known as conformal mapping or conformal transformation. So two transformations did exist. One was by Schwarz-Christoffel and was this Zukowski transformations. And for shape symmetry, especially along the x-axis and the y-axis, one is x-axis is for the vertical directions and the y-axis for the lateral sections, we have to deal with a series of mathematical series. Now, in order to use this mathematically, when you have a big series, is very difficult to deal with from a practical standpoint. So what was done was that entire series was truncated to only 3 distinct terms. So why? Because we need only 3 terms for a section to define itself. One is typically half breadth, the draft, and the cross-sectional area of the section. And that is enough when we have 3 terms in this, and these 3 terms came to be known as Lewis transformation or Lewis conformal mapping. And then using the optimization technique of Newton-Raphson method, so what they did, minimize the transform section to the original section by the least square method of finding the distance between the transform section and the original section here. So in conclusion, we can say that this conformal mapping did have a profound effect on sea-keeping or determining the sea-keeping or motions of the ships. So you can wonder that what this conformal mapping has actually done to the benefit or to the benefit of naval architects today, what would they be without the existence of conformal mapping? The benefits they have derived from conformal. So the conformal mapping had a tremendous impact on finding the sea-keeping motions or motions of the ships. So that brings to our paper what we have done. This is nothing, in hindsight, I thought that, okay, this is not a fantastic achievement here. What we have actually basically done is, why is it not going forward? It's not going forward. All right, okay. So what we have done is essentially took the strip theory, coded that in MATLAB, and trying to see whether it can matches with the experimental values. Now, we all know that most of us use Maxsurf motions module to predict the motions. I mean, one did not even know what the underlying theory is and what it is doing and what it's not doing to understand that. As long as we get our significant heave, significant pitch and roll, we are happy with that. But let's see that whether this procedure is giving another process to find this. So essentially my topic is going to look at the introduction, which I have already said. We have taken AME-CRC series. That's because I have dealt with AME-CRC series since 1995 onwards, and several papers were written by me regarding AME-CRC series, resistance, motions, converted the AME-CRC to Catamount and Hull forms, did another set of resistance and motions and all that stuff we did. We'll look at Lewis conformal mapping here. Then we'll look at the hydrodynamic coefficients, how they were calculated, the strip theory, a little brief about the strip theory, and computing this 2 degrees of freedom of ship motions in frequency domain. Finally, we'll come to some results and conclusions here. So introduction is, aim is to validate the frequency domain sea-keeping code presented in this paper. So what we are doing is, we have done that MATLAB code. We are going to present some of the results of that along with the experimental data which we had for AME-CRC series. And AME-CRC, I'll also give you a brief about the AME-CRC series. So of the series that we are dealing with. So we are presenting only right now the arouse response amplitude operators for the AME-CRC hulls against head sea conditions, because that was the only experimental data we had. So if it appears to be good enough, then we can also use the same code for following seas and oblique seas and beam seas as well. So results were compared against experiments, and we'll go through some of this. And this is the model of the AME-CRC series. AME-CRC series consists of 14 models, and they have a L by B ratio from 4 to 8, by T ratio from 2.5 to 4, and CB values from 0.4 to 0.5. And there were a lot of industry participants, including AMC and UNSW Sydney and UTAS in Hobart. There are a lot of people, including University of Western Australia in Perth. They were all involved, plus a lot of several industries, including that time it was called Tenix. Now it is called different, right? In Melbourne, Tiles, right? Tails, right? And then we also had this Garden Island industry also there involved. So a lot of people, a lot of effort has gone into developing this AME-CRC systematic series to see how it can be used for. So good thing was that I was in charge of that particular program in the CRC when it was there. So I have used this to, and people have actually taken this and the data and actually did consultancy work for that based on those published data and internal reports. So from the AME-CRC, we have taken 7 models, and the 7 models are published here. As you can see, we have not taken all the 14 models, and all the 7 models were analyzed for regular head waves at 2 different Froude numbers, 0.285 and 0.57. And the coefficients that we use in the manual were calculated in the frequency domain and with the developed code, and then subsequent analysis were made. So Lewis conformal mapping method, as I mentioned earlier, it is trying to find between the transform section, because Woodsell's procedure was circular cylinders, circular sections, but the ship shape is not a circular section. So it has to be, we have to do the mapping here. So in order to calculate these hydrodynamic coefficients, we have to have added mass damping coefficients. The cross section of the hull has to be mapped. And this is the effect of mapping for model number 3 at section number 20 and section number 30. Pretty close. You'll never get exact, because I have seen with published literature, it is never exact, but it can be very close because of the Newton-Raphson method, which has been used to optimize by the least square method to make sure the distance between the transform section and the actual section is minimal. So Ray was talking about mathematics. So here's the amount of mathematics that we have. Multiple expansion theory, conformal mapping method, and integral equations are coded to calculate the hydrodynamic coefficients. This is the entire maths. I'm not going to elaborate on that. There was plenty of maths in my initial stage, which I am all skipping all that to go further. So you will find that we have to see that the convergence occurs. So there are two components here, P2M and Q2M, and it has been found that when M is that limits, when M is approximately equal to 7, the suitable convergence happens, and that's where we generally stop. And the sectional hydrodynamic coefficients, like the added mass and the damping coefficients, are then calculated based on that mathematics that which I showed you on the previous slide. So we have this added mass and damping coefficients calculated here for them. The sectional hydrodynamic coefficients are now, as you can see, they're similar, and you can go through the literature. In the literature, you'll find similar curves, which are published, especially in the dynamics of marine vehicles by Rameshwar Bhattacharya. You will see that for all these type of similar curves, you will come across looking at the hydrodynamic coefficients of ships. Now, this is for the sectional damping coefficients for section 20 and section 30 for that model number 3 here. As we are not presenting all the models here, but some examples of those here. Added mass and damping coefficients. The hydrodynamic coefficients for the heave and pitch motions of a ship can be readily estimated using the strip theory method, which you all know. So the global hydrodynamic coefficients are obtained by integrating the entire added mass and the damping coefficients over the entire length of the ship, which we all know. And they are the expressions for calculating the added mass and the damping coefficients for the entire ship throughout its length. The integral sign implies that we are integrating over the entire length here. So now we have added mass and damping, global added mass and damping coefficients at fruit number 0.285 for this model number 3. And we have used the salvation method here, the damping for the cross section, the global excitation wave terms, because unless we know the wave terms, we are unable to calculate the forces. So that is why we have used the salvations method to compute the excitation force, which is now applied here. So you can see that there are a fruit kilo part, there's a diffraction component, etc. So this is the mathematics behind it. We are not going to touch this here under any circumstances, but they are the excitation terms in heave and pitch. The left one is on the about the heave, the right is about the pitch at different frequencies from 0.5 to 1.5 hertz, and at fruit number 0.285. So now in frequency domain, when we match, this is the mathematical model which is created to calculate the vertical motions and pitch motions and pitch and heave motions. Because the 3 represents heave and F5 represents, the subscript 5 represents pitch. So we have this. So it has to be, in order to allow the response amplitude operator, it has to be developed into a matrix form. So in this matrix forms, we have all the components which are going there with the X, and then we have the external force. So once we have this matrix resolved, we get to excitation force. And finally, we obtain the heave and pitch motions by this. So X3 represents the heave, X5 represents the pitch, and pitch rho is given by non-dimensionalized with wave amplitude and the wave number. And similarly, the heave amplitude is also non-dimensionalized with wave amplitude. And the vertical acceleration is also non-dimensionalized by using the frequency and acceleration due to gravity here. So some of the results that we are going to see here are this. So that's the results for model number 1 at 0.285. That shows you the experimental data is the circular dots, and the red line is actually from the coding. You can see the experimental data and the code, which the results produced are almost, it has a good match. Will not say exact, but at least a good match. So it gives us confidence that this results seems to be reasonably well done. So similarly, we can go for model 1. This is for the pitch here, pitch row here. That is the heave row, pitch row, and the non-dimensional vertical accelerations shown here, and seems to be a pretty good match with this. So, and this is for model number 4. Similarly, at point number 285, heave row, pitch row, and added resistance here, vertical acceleration here, or non-dimensionalized 0.57. So in conclusion, the test results of emission series were examined to validate the sea-keeping code developed in the frequency domain which we have developed. The numerical data were compared with the test data and taking into the uncertainty of experiments. Now, we want to know how good is the experimental results. It is a known fact that however well you do your experiments, there might be some level of human error which might creep into it, and your data may not be as good as you think it is. And we think that the deep motion program that has been developed in MATLAB performs quite well in predicting the heave, the pitch, row, as well as the non-dimensional acceleration of that particular sections here for the global movement. So it has provided, and we are happy with that. And as I mentioned, this is going to be presented at PRADS 2022, and it was supported by this by Yildiz Technical University, where I have also spent 2 months of sabbatical leave to do some teaching. Thank you very much.